electrical mixture of trapped ytterbium plus and a neutral lithium system.
Yeah, thanks. Thanks for the introduction. And my name was actually close enough. Try pronouncing Christian Huygens. Vincent van Gogh, indeed, for that matter. But yeah, so I want to thank the organizers and also the institute for giving me the opportunity to speak here. I had never been to Boston or Harvard, and it's very nice to finally visit. It's a good opportunity to see some old friends and perhaps make some new ones. Yeah, so I work on atoms and ions. This cartoon is very old. I made it when I was still writing grant applications. So you could argue that it has delivered me a lot of money, this little logo. I always draw the ion to be very big and the atoms very small because, as you will see, I work with ytterbium, which is very heavy, and lithium atoms that are very light. Of course, if you look at the radii of these particles, then the ion is much smaller than the neutral lithium atom, but okay, that doesn't matter, I guess. Oh yeah, oh sorry, just let me go back. Yeah, actually, okay, I have to apologize beforehand. Yeah, I will mostly show you two-body physics, but I'll try to, you know, get the third body kind of in there in our experimental results. Okay, so in Amsterdam, I run actually 3 trapped ion experiments, some of which is aimed at quantum computing and optical tweezers. So we got quite distracted by this work. Corrupted, some people may say, I guess. And besides this, I also have my atom ion experiment, which I will talk about today. Okay, well, this has been shown so often, so I can browse over it. And so we have an ion, we have an atom. The ion polarizes the atom, so I get a charge-induced dipole interaction, as I prefer to call it, which is just the square of the electric field here of the ion. So it's 1 over r to the 4, because it's second order perturbative. Now, when people started, I think this field really originates mostly from our cold atom friends. And of course, they're always very, let's say, preoccupied with scattering lengths and reaching the S-wave limit. And I think from the onset, it has been quite clear that, you know, if you want to reach this type of S-wave physics that they use in BECs, etc., it is a little bit hard for atoms and ions. So if you look at most atoms, and of course we prefer the alkalis, which are the biggest, of course, and they have the largest polarizabilities here. They're all of kind of the same ballpark. The ions, of course, we prefer always the earth alkalis, like the barium. In my case, the ytterbium, that looks a little bit like an earth alkaline ion for its lowest states. And if you then start computing what type of energies, collision energies you need to become S-wave, then you see that for many of these species involving heavy atoms in particular, this becomes quite challenging. You have to go to the nano-Kelvin regime, even for cold atom people. That's not something they do on a daily basis. Trapped ion people, they work at preferably much higher temperatures. But it helps to have a light atom and a heavy ion, or vice versa for this story. But it turns out that it's better to have the atom light and the ion heavy. And this has to do with the fact that the ions are trapped in a state-dependent, or sorry, in a time-dependent potential, namely the Paul trap. There has been a lot of bad publicity about the Paul trap, I guess, in my field, because it is the cause of the fact that the ion temperature tends to be not the same as that of the atoms when we trap them together in this field. And in fact, the ion temperature is much higher. So you call this micromotion-induced heating. And that's why some people want to get rid of the Paul trap. No, this is not me. I love the Paul trap. Paul traps are amazing. They can be tens of thousands of Kelvin deep. You can trap ions for months if you want. So I like the Paul trap. So then to deal with it, I need to choose an atom, an ion that has the right mass combination. So in this case, this was actually well, Marco Cettina, who was back then at where was he actually? With Vladan Vuletic. So he figured out then, together with Vladan, that you need a light atom and a heavy ion. And then looking at the periodic table, then in my humble opinion, and also theirs, by the way, the best choice is lithium and ytterbium. So ytterbium is the heaviest ion that you can, let's say, straightforwardly manipulate with lasers. And lithium-6, of course, because 6 is much smaller than 7. Yeah, it really helps in this case. So we use the fermionic. That's the lightest atom that you can, let's say, manipulate with lasers. And actually, if you think about it, I did not know it at the time. I did not bother really looking into it. It's kind of a funky choice, yeah, because of course the ground state of this guy with lithium is that lithium is charged. Yeah? So you could expect like charge transfer here. Luckily, it doesn't occur very quickly. A much better choice is, of course, the one that Tobias uses, namely barium plus and lithium, because then you're in the ground state and there cannot be charge transfer. Having said that, barium ions, of course, have as a disadvantage that the collapse of the d orbital is almost complete. Yeah? So the d state is almost the ground state, which causes large second-order spin-orbit coupling, and this has effects on the spin dynamics of the system. But yeah, that's just to show off that I know something on my system. Okay, so then we build it. So we combine, some of you may know Selim Joachim from Heidelberg. I took a train to Heidelberg. I said, look, Selim, I need to build lithium. He's an expert. So he gave me basically drawings of his setup, Seemann slower, Feshbach coils. I did not know all these things. And I just made it a little bit wider to put in this big ion trap here. It's like this, so I can trap ions and also have a cloud of lithium atoms. Now, of course, then many years of work, but in the end, it turns out that we have this. We have a small cloud of lithium atoms that are very cold. And of course, it's a fermion. So for those in the know, you need to make spin mixture, otherwise you cannot evaporatively cool it. And so lithium-6 has a nuclear spin of 1, so we're in the ground state here. Yeah, and then the ion is here, it's just Doppler cooled, so it's relatively cold, let's say half a millikelvin or something. Yeah, and then what we do is we simply transport these atoms up. And they're in optical dipole trap, so we have some piezo mirrors, put them on the ion. We wait for a bit, do our stuff, and then we throw away the atoms actually. We just look at the ion. And one of the first things that we did is seeing, okay, do the atoms actually cool the ion or not? And this is something we could see quite nicely. And so we started the Doppler limit, and then you see that after a while, the ion gets colder and colder. Well, this time scale is very long. It takes 1 second. This has to do with the fact that we have a very low density. You see the atoms were like, what was it here? I think 10 microkelvin. You see, indeed, Marco Cettina was right, and also others like Hans Demelt, who already knew this. The ion does not reach the temperature of the atoms, so it remains considerably hotter here, like it reaches 100 microkelvin. Still, this is quite nice because I think this was the first time since, let's say, the days of Demelt, that buffer gas cooling outperformed, let's say, Doppler cooling, right? So we were quite pleased with this. Did we reach the S-wave regime? Well, kind of. We're right on the crossover here. So we're kind of on the edge where, the angular momentum in the collisions is quantized. Okay. Well, can we see this then? So to figure this out, we did an experiment in which we look at spin exchange between the ions and the atoms. So, sorry, there's only one ion. So between one ion and a cloud of atoms. So for this, so we use 171. That's also it's a famous qubit. It has a nuclear spin 1/2. So we have this FS1 state here. So we use a microwave wrap here to put it there, and then we wait for a bit. and then it can collide with lithium. And yeah, since the spin orbit, second order spin orbit coupling should be relatively small, the spin is mostly conserved, so the atom has a few options here to exchange spin with this ion. Yeah, unfortunately, there's one atom who does this in a cloud of 10,000, so we don't know which one. So we cannot see this, but we can measure the ion very well. So we can just look on the ion afterwards and see if it has exchanged the spin. Yeah, and we do this by shelving this state to a very long, and we shelve it to the F state, which lives for 1.5 years. So we have plenty of time to see. And so this is really a quantum jump experiment that is extremely accurate. And you know, that's one of the reasons, of course, also that trapped ions are considered in many quantum technology settings. Yeah? So we can detect this very well. Okay. Now, and what we did then is we add an electric field, push the ion slightly out of the center of the trap, and then it's in this oscillating field of the pod trap, so we can tune the collision energy. And if we do this and we look at the probability that this spin flip occurs, then we see that it's not flat, there is actually some structure. And of course, back then we were still naive. Or perhaps I'm still naive, I don't know, but I would say, you see, it breaks the Langevin theorem. Langevin theorem should say atom ion, you know, it's like a chemical reaction, it should be flat, it should not depend on energy. And so I went to my favorite theorist of the day, who was Michał Tomza. Well, he's still one of my good friends, of course, but he fitted this then with his scattering theory, and based on this, he could figure out both the singlet and triplet scattering length of the atom-ion combination. So I think this is probably the first time that we measured, well, it's not very accurate as you see, but we got some kind of estimate of the singlet and triplet scattering length. And they're very different, and that's also reflected in the data. We think basically every collision results in spin exchange in this case. So it's a very fast process. I'll get back to this later. Now, the atomic density is extremely low in our system. So it's 10 to the 16 per cube per meter. So that means, you know, when the atom and ion collide, there's absolutely no other atom even close by in the vicinity. So it seems up until now I went to the wrong workshop, I guess. So, but of course I could try to, you know, BS my way out of it. No, well, I have something here. Okay, let me first explain why free body actually is very interesting and why I would like to achieve it. Yeah. So this has to do with my friend Tobias Schetz, who is sitting there and giving a talk tomorrow, because he has found Feshbach resonances between atoms and ions. And he did this by looking at enhanced three-body laws at particular magnetic fields. And of course, I always also want what Tobias has, so we're looking for this. Okay. But at the moment, back then at least, we did not have this density. But I had an idea. I can, of course, convince one of these atoms to get a friend. So I can do this because it's lithium, right? So many of you will probably know that lithium-6 has a huge Feshbach resonance between, so this is between the atoms now. It's at 832 Gauss here. Yeah, and my idea was kind of, you know, I was doing some math and also talking to Jesus. If you now look at these Feshbach dimers, they're kind of funky things, you know, because they're quite big. They're kind of like the size of the scattering length. So if you go close to resonance, it can actually be very big. And of course, on the other side, on the BCS side, you know, you don't get these dimers. You get something else. But yeah, but what is now interesting is that you kind of get a crossover now here from a molecule colliding with an ion to actually, like individual atoms colliding with ions. And actually, you can calculate where let's say the typical, well, how do you call this? Like the R star, you know, like the typical scattering length between the atom and ion, the natural unit of this, and where it becomes identical to the scattering length of the atom or the size of the dimer, or to put it differently, where the binding energy of the lithium dimer, because they're very weakly bound, gets the same as the S wave, let's say, energy of the atom-ion combination. So you get a very strange crossover, and it's very reachable because it's at 704 Gauss, and these binding energies are like in the microkelvin regime. So, and the typical ranges are like in the it's like roughly 70 nanometer. We're talking about. So yeah, I think this is very interesting regime to study. One that we can do in the lab. So okay, so I went to Jesus and I said, okay, I need to know what happens here. Of course, it's always nice in a talk to tell it in the logical order. The real order was that we lost ions when we were evaporating close to the Weschbach resonance. But still, we needed to understand it. So I went to Jesus. I said, look, this is a complicated problem. It must be very quantum-y, so help, please. And then I was always very surprised that Jesus says, yeah, just calculate it classically and see what comes out. Okay, so that's what we did first. And I think it gives so much intuition that he was, of course, absolutely right. So one of my PhD students who was very talented, Henrik, under the supervision of Jesus, started doing molecular dynamics calculations. So we then assume now a gas of lithium-2 particles that are bound together by a van der Waals force. So it's a Weschbach dimer, so it's very weakly bound. So it's highly, let's say vibrating, and but it's not rotating. Weschbach dimers, they don't rotate, so it's kind of a funky thing. And then we let it go, and it could bounce onto an ion. And we took the full Pol trap into account. So all these oscillating fields, everything was there. And we put in a million different, parameters, like a temperature for the dimers, a temperature for the ion, different Pol trap parameters, and we were looking at what happens. Now, what you see here on this x-axis is the ratio of the collision energy to the binding energy of the dimer. And here you see the rate that we calculated. Now, the dashed line here is the Langevin rate. So what you see here is actually two processes. One of the things that can happen is the formation of a molecular ion, and the other lithium atom flies away. And here you can also have that the ion breaks up the dimer. So if the collision energy is very low compared to the binding energy, then actually it turns out that you basically always get lithium, ytterbium molecular ions. Whereas if it's the other way around, then most of the time the ion simply breaks up the dimers. So I think it's quite intuitive. It's nice though that the molecular dynamics simulations could be, despite all this time dependence, etc., could be explained over all these orders of magnitude by simply basically the Boltzmann factor. So it's very easy. In the end, it was kind of very easy to understand. Of course, this is classical. If it would be quantum, then for sure there would be structure in there. Okay, then we did the experiment. So now the idea is that because we can actually not go over the Weschbach resonance, so this is the one time in my whole talk that three-body interactions or three-body collisions will play a role. The idea is we go close to the Weschbach resonance, and then the lithium atoms will occasionally have a three-body interaction, and they will form dimers, and the other atom flies off. That's how you make the dimers. So you have a cloud of atoms with a very few dimers in it, and then we look at dimers. So we produce them at 700 Gauss. So that's the thing that happens. Okay, so then we do this, we wait for a while, and we see, is there an ion by simply scattering light? The dipole allow transitions, and then we would see, sometimes there is light, so this is detection time, this is number of photons. Sometimes there's no ion left, and sometimes, it would be gone and reappear. So we think that our idea was then, well, perhaps this is the molecule then, perhaps this also, but this could be the molecule, and we dissociate it again, and then the ion starts to give off light again. Okay, so to test this, then we started shaking the Pol trap. So the idea is so we put on some field here to oscillate. And then, yeah, and then we see that if we hit the right resonance, which is at 183 point something kilohertz, then boom, we lose ions more often than otherwise. And yeah, we can calibrate now this. So this is like well, it's not parametric, I guess, but we shake the trap and the ion flies out if it's resonant. But of course, this resonance depends on the mass. So we could figure out that we have exactly a mass of 180. So we conclude that it's ytterbium-174 and lithium-6 bound together. And the nice thing is ytterbium has a lot of isotopes, so we can also calibrate this very accurately. So we're very sure that we make molecules. Okay. Well, of course, it could still be that we did not get our density right, and we do see three-body recombination. This could be one of the things happening, or it's the dimer. So this we needed to figure out. So what we did is we changed the atomic density, and then of course the three-body recombination should scale with it in a particular way. And yeah, so here we see the atomic density that we have, and we see actually that that amount of ions that we lose actually goes up. Yeah? So it goes the other way with the density. So we're absolutely sure that we see this process happening here. Okay. So the other thing we changed then is the magnetic field, and this changes the amount of dimers that you create. So here we see the amount of, well, we call it the probability that we have a dark ion as a function of the magnetic field at which we make the dimer now, yeah? So all the collisions happen at 0 Gauss. And you see here now the data of the ion, and also you see also a theory curve, and that's now based on the well-known rate equations for the formation of lithium dimers, and that's actually already quite old, this theory, without fit parameters. So we actually really can measure this amount of dimers, and it fits exactly. The only assumption we make is the Langevin rate. So every collision between an ion and a dimer results in a molecular ion. Yeah. So, and of course, there's also thermal equilibrium theory for the dimers. Yeah, that only apply close to the Feshbach resonance, let's say. Yeah, so we were very very pleased with this. And what is kind of telling, I think, so if we show it. So if you take, for instance, this point here, because it's again a quantum jump measurement, so we're very accurate. So we could measure this now at yeah. So this point corresponds to, let's say, 50 dimers in a gas of like 10,000 atoms. So this, I think it would be very hard to detect this amount in some other way. Yeah. Okay. And the only thing I assumed was the Langevin collision, but I think this makes perfect sense from my, let's say, naive experimental point of view. So if you have an atom-atom potential, it's 1 over r to the 6. The atom-ion potential is 1 over r to the 4. So the density of states in this one is much higher. So it's no surprise that if you have a collision between these two, that then actually the ion steals 1 atom. So that's, I think that's completely logical. Yeah? So up until now, and this is the famous plot, of course, from the review of modern physics, that shows the energy levels of lithium. So up until now, we were making this this dimer somewhere here, and of course we scanned the magnetic field to 0 before we let it interact with the ion. So the dimer was like a nanometer, I think, here, and the binding energy you see is like a gigahertz. It becomes completely singlet. You see, it's no longer reacting to magnetic fields, and that would be very cool now to also study this regime for much larger dimers. Okay. Then, I think I'm almost out of time already. Let me just quickly say something about sticky collisions, or let's say the complex formation in atom-ion collisions. I think this is, I was already talking about the Langevin theorem, and I think it has been true in our field that the trap of the ion trap has well, overlooked is not the right word because people did consider it obviously for the micromotion heating, but I think its full implications were only later kind of realized. Of course, Marco Cetina again was one of the first who looked into this type of sticky or well, this complex formation when an atom and an ion collide and the ion is trapped. So he had this famous trajectory in his paper where you see the atom comes, it collides with the ion, and then you get various bounces before it flies off again. I think me and many others in the field always associated this with the micromotion of the ion, but this is not true. What actually happens is, well, I think you probably know better than I do, but there's an ion that is very strongly trapped, you know, and there comes an atom at low energy, it collides with the ion starts vibrating in the trap, and before now the atom has lost energy, right? So it cannot escape anymore. So it just collides again and again and again. And actually it's worse if you have a time-independent trap. So this happened quite a lot. And again, together with Jesus, we started looking into this. And I should also say that Rui Ozeri at the Weizmann Institute, he also worked on this and also got some experimental data. Now, what I want to point out now, which I think is very important in our field, is that it's somehow a very unfortunate thing, you know, because it's worse or if you get cold. So it's an effect that starts appearing as you go cold. So that means that it's very, very easy to confuse it with a quantum effect. So we have to be very, very careful here. So it has an effect on the rates. That's what we think. Yeah. So what so I will not talk about the details right now. I just want to say that I had again my student Rene Gerritsma. He did these molecular dynamics calculations again. So it's purely classical. Looking again into what happens if we have atoms now colliding with our ion in our trap. Thank God these effects are less severe when you have a large mass ratio like we have. But if you look, so I had this plot of the spin flips back then, but when I was celebrating that it did not follow the Boltzmann theorem. So we came up with like a simple model looking again at the rate of collisions now between the atom and ion. So this is now calculation, it's not data. And if you kind of, you know, making an assumption about the spin flip rate, obviously, but if you put it on it, then you see that we were actually quite lucky because the classical effect goes up, but my effect goes down. So I still stand with that it's quantum. But I am the first to admit that this was a lucky escape in a sense. Yeah, so that's then the theory of trap-assisted complexes in ion-atom mixtures. Okay. Actually, it will have other effects. One of the things that is also something to worry about is that it will probably, well, for you, I guess, for this audience, it's not so important, but it will also mean that probably buffer gas cooling has also another limit that has not considered yet. Because even if you have the right mass ratio, even if you do everything well, even, by the way, if you don't have a Paul trap, but a static trap, at some point, these atoms will stick to the ion, which means at some point another atom will come and then the whole thing dies. So that's another limit to buffer gas cooling. Okay. So what about Feshbach resonances? Well, we are looking for them. And I really wanted to present them here. I cannot yet. Let's hope they exist. But so what we did to increase the density is we made a dimple trap. So now we have we have a very elongated optical dipole trap, and we shine in an additional laser. And this is actually a picture of it. So you see actually it's very dense because of this this interference. Had this fringe around it. So we think we are denser by a factor of 10. So this should mean that we are in the range now where we should see them just like two beams. Okay, I will not talk about micromotion. And then I will leave it at this. So I have showed you some chemistry here talked a little bit about complexes and no Feshbach resonances yet. This is us. And for the ion trappers amongst you, I want to still advertise ACTI, which I organized in Holland in September. If you don't know what ACTI is, then don't worry. The ion trappers will know. Thanks.
Very nice talk. So, I mean, you discussed about that you need this experiment where you collide the ion with the molecules, that you need the molecules in order to see. Did you actually go above the Feshbach resonance where there's, you know, no molecules? Or, I mean, it seems to you always, like the magnetic fields that you use, you are below the Feshbach resonance. The simple check would be just to go above 830 or something, and then you know there shouldn't be Feshbachs, yeah?
Yes, no, we haven't. And this has to do with the fact that it's at the very, very limit of what we can do. Let's put it like this. So I have fried these coils several times. I don't. I've once I have the Feshbach resonances between atom and the ion, I will do it. Yeah, it's at the moment. Sorry, it's a bit. We're a bit anxious.
I can understand this very well. When you are doing this heroic spectroscopy, are you doing this at these high fields? Or are you switching fields? Well, if you're driving transitions to see your ytterbium eye.
Oh no, always at low fields.
And you always switch these large magnetic fields. So how fast can you switch these fields?
Yeah, not so fast. Actually, the coils are fast and all the switching stuff is fast, but the ion trap slows everything down. There's so much metal there that we cannot switch very fast. But even, when we do the spectroscopy on the quadrupole transition, we even rotate the field in such a way that you get the optimal Clebsch-Gordon, let's say, transition. So but of course, if you switch fast, then the stability is a problem actually, and that's something we are now finding out. We want to very accurately measure, for the Feshbach resonances. So we use the ion as a probe, and it's well, we talked before. It looks very stable until and then and then of course, if this happens, then this is a disaster. We will not find the resonances.
Yeah, thanks so much. In the experiment with the molecular dimers, with the lithium dimers, you discussed this in terms of the Langevin theory, right?
Yeah.
Now I forgot if you also measured the rates or only had the calculations of the rates. But my question actually is, can you make these dimers large enough that the cross-section or that the extension of the molecule will be larger than the relative and input parameters for the Langevin theory, meaning the cross-section could be larger than capture because the molecule is a much bigger object than its Langevin cross-section.
Yeah, so what we at least see in the theory here is that,
I think in this one.
Yeah, so the molecular ion creation rate, let's say it saturates at Langevin here. Yeah. But of course, the other one where it breaks up the dimer is unlimited, right? So this can happen over a very large distance. Yeah. Because also glancing collisions can do.
But I mean, is it possible that you can that you can manipulate this by making the Feshbach molecule smaller or larger? You can go, closer to the resonance and further away, and you can change the bond length, right? Or you can make essentially the dimer a super halo type dimer or a much more compact dimer. Yeah. And I'm wondering if that has an effect on the cross section.
Well, in a sense, this is it, right? Is it? What you say, you're right, because here if you get a very small binding energy, you have a very large molecule, right? Yeah. So you see that indeed now you're left with some fraction of the Langevin rate here. So yeah, in a sense, but of course this is classical, and you could wonder how well this works at some point at these very low energies.
I have one technical question. So you're changing your ODT power to change the density of the atoms in your experiment, right?
Yeah.
So I remember yearly when you do that, the temperature of your ODT also changes because phase space density is conserved. So does that introduce any sort of extra considerations?
I think here, so I know that part of my talk was about that the Langevin theorem doesn't hold, but we still kind of work on the assumption that it mostly holds. So temperature, fluctuations or differences should not matter too much for the rates. In each case, the other thing is, of course, that, well, let me not go through it again. It's a quantum jump measurement, and it only jumps one way, right? So once it's gone, it's gone. It's not like when you wait longer, that's something else. There's just one ion. The whole talk, there was just one ion.
Yeah. The same ion in all your experiments.
This I cannot guarantee, but
You said you could try for months, so.
not if it turns into lithium ytterbium, unfortunately. Yeah.
So
Any other, yes.
how well do you know the position of the flashback resonance, where to look for?
For the atom and ion, not. We only know kind of, from me how TOMSA we get information like there's one below 10 Gauss, which is like a nu equals, a least bound state. Yeah, or you're unlucky, and then it's between 10 and 50 Gauss, and it's the second bound state, but then it will be narrow, etc. But we're kind of hoping that we will be lucky in a sense. Well, lucky. I mean, we're not quite S-wave, right? So I think Tobias, perhaps he will talk about it tomorrow, already saw also other partial wave Feshbach resonances. In fact, if you look at the spectra that he measures, then you see very many resonances. So we were kind of thinking that, if they're there, we should see them, basically. So that's our working hypothesis. Of course, there's also an option to not look at three-body, but to look, for instance, at the spin exchange as a function of magnetic field. But I'm a bit anxious to do it because it is already so high. So we already have like basically Langevin rate for spin exchange. And yeah, it's hard to imagine it getting much larger, right? So it looks like a tiny signal to me then. I'm not so, of course we can use other spin states, etc. We could also change isotopes. But for the atoms, it's hard, right, to go to the boson, because then everything changes kind of. And for the ion, it doesn't matter, fortunately, which one you use, because the reduced mass completely depends on the atom. So all of the atoms, all of the ion isotopes will have the same resonances, except 171 that has a clear spin.
Why it's better for lithium-7? Better prediction, or?
No, it's not
Switch.
better. It's just to diversify, let's say. Yeah, let's say you look and you don't find them. Yeah. But I think, I mean, in general, the prediction is, of course, because it's very long range. Yeah. Okay, I don't even want to pretend I'm an expert in these kind of theory things, but it's very long range. So I would imagine that there are quite a few resonances. The density is quite high. It's not like lithium, you have 1,000 Gauss and there's one. Okay, it's a very thick one. Well, there are two actually, but it's one very thin and one very thick. But there should be many, many more. That's the prediction. But to get like, I think Michał Tomsa, he claims that he can calculate scattering length of lithium with lithium, or lithium with lithium plus, that type of stuff. But ytterbium, when you deal with it, even if you want to describe the atomic levels, you need 15 valence electrons, right? So it's just not. I mean, sure, the S state is easy, but once you go a bit higher, you get all these electron configuration, huge spin orbit. I think it's much more complicated area.
This is more of a theory question because it's a theory slide. Maybe Jesus should also. So these are classical molecular dynamics calculations, right?
Yes.
So most of these ND type classical calculations require parameterization of the force fields. Now, were the parameters available for lithium, ytterbium plus, for instance, or were just used for generic atom ion type?
Yeah, so we use you mean like the polarizability of lithium?
Well, yeah,
Yeah.
no, the polarizability of lithium, I understand, but I mean, you know, these MD, I assume, I don't know what sort of a molecular dynamics package you use, but they are based on parameterization of the force field.
Oh, yeah, you mean the short range part of the.
Well, for the interaction between the,
Yeah, so we, yeah, of course, the long range is well known, right? Polarizability, but for the short range, so what we did when we developed this code is we basically assume a 1/r⁶ repulsive potential, which we took closer and closer and closer until we saw that let's say the average observables converged, which means the temperature actually. So we see at some point when you look at because we normally use it to simulate buffer gas cooling between the atoms and the ions. So we see that if you take this repulsive barrier closer, then at some point the temperature remains the same. It doesn't matter anymore. But the individual dynamics, which is another topic, it's chaotic. Yeah, which at first, we were confused because it's basically one particle problem, right? But again, the trap, of course, adds the second particle, let's say, so it becomes chaotic. So then this never converges. I think this is a horror story. For the atom, I frankly don't know. I think it could be that this potential is just well known, or I really don't.
We took it from Johannes' paper, I believe.
Oh yeah, so we just blame Johannes. Well, that's good.
No, like this is very accurate potential from spectroscopy. Okay, it's very good potential.
That's very good.
All right. There are no further questions for now. Let's thank our speaker again.